Hello and welcome back to another episode of Squaring the Circle. Let's begin after I put my headphones on. There we go. All right. So we have been talking in recent episodes about cosmic impact phenomena. We've been looking at the Tunguska event, which occurred in June of 1908. We covered that pretty thoroughly. Then we had a couple of episodes where we were looking at the proximity of near-Earth objects and close flybys that have occurred in the last 3 or 4 decades, and have learned that those types of close encounters have occurred way more frequently than anyone would have imagined a generation or two ago. What I'd like to do now is get into the actual impact cratering phenomena where objects from space strike the Earth, and we'll take a look at a little bit of the evidence that it's accumulated over the last few decades for the formation of craters and astroblanes. Let's talk about the difference between the two. A crater generally, now there's obviously overlap in the definition, but a crater generally is an open bowl-shaped structure or depression that we can actually see in the landscape, and it's quite obvious, such as Meteor Crater in Arizona near Winslow is the type example that we would invoke in terms of a classical crater shape, where you have a bowl that was excavated into the Earth by the impact, the actual surface impact of an object. Remember, the Tunguska object was an atmospheric impact. It detonated in the atmosphere. So what we're going to be looking at now is the geological consequences of actual impacts into the ground surface itself. And we will look at, in this episode, what I'd like to do is just sort of introduce you to the broad spectrum of impacts. We're going to be looking at a sample of the almost 200 now confirmed impacts that have been recorded in the geological record of the Earth. And then we will be looking somewhat at the biological consequences, but that will be primarily a focus of another episode of Squaring the Circle, in our efforts to completely unpack this whole phenomena of cosmic encounters, what it means for life on Earth, what it may mean for the geological story of the Earth, and what it may mean ultimately for the story of civilization, human civilization on Earth. So let's get right into it. And first thing I'm going to do is I'm going to make an obvious connection here. The connection between natural phenomena, impact phenomena, cosmic phenomena, such as we've been talking about, and some of the traditions that have come down to us through various mythic and religious and legendary sources about events that have happened in the past. So I'm calling this Unsealing the Apocalypse, because once we get into the legacy that we have inherited of past traditions, I think we're going to begin to see the quite striking and extraordinary parallels between the accounts of these events that have happened in recent times, where people have lived to recount their experiences, such as we saw, I think, very clearly indicated in the stories coming out of the Tunguska event of 1908. We're going to see that there's a very strong correlation between the imagery of myth and legend and folklore and traditional sources and accounts, as there has been from the more recent scientific and eyewitness accounts of cosmic phenomena. So I'm calling this Unsealing the Apocalypse, Cosmic Catastrophe. So let's jump right into it. We'll begin with a gallery of impact craters and astroblemes. Now, an astrobleme, as I was talking about, is a little different than a crater. It means star wound. And an astrobleme is an impression in the landscape, the planetary landscape, made by an actual impact, but it's not so evident. It's usually highly eroded. Sometimes it's completely buried under sedimentary rock or other depositional material. And so it's not really visible too much from the surface, but it's still there. Ground penetrating radar and LIDAR surveys and so on are showing up things that we don't really see too visibly from the surface that have been laying there hiding just beneath the surface for in some cases millions, even billions of years. So it means star wound. It's think of it as a scar in the landscape. So crater, the hole in the ground. An astrobleme is a scar on the Earth that may or may not be readily discernible. All right, so the phenomena that we hold responsible for this is usually the impact of an object from space, typically an asteroid, and an asteroid can be a variety of things. It can be carbonaceous, which is roughly the density of a typical rock that you would find, a typical sedimentary rock that you might find walking along a creek bed or, a river bed or whatever. An iron asteroid is going to be much closer in density to a piece of cast iron. And of course, their consequences are going to be different. A smaller iron asteroid can deliver as much kinetic punch as a much larger carbonaceous chondritic or stony asteroid. So at the lower end of the spectrum was what we began this conversation about, talking about the Tunguska object, which was probably not much more than the density of ice. So each of these kinds of materials is going to have a different effect when they strike the planet. In the case of low density, like Tunguska, they might, and small enough, they're not going to make it to the surface. They're going to blow up in the atmosphere. The denser the object, the smaller it can be, because it's more capable of penetrating the atmosphere to strike the surface. This particular graphic here is pretty cool because what it's showing us here is what I believe ultimately we're going to be moving towards, is the idea of a simultaneous multi-impact type event where you have a comet nucleus or fragmenting or an asteroid breaking up. So it's not a single impact, it's a multiple impact event. And I think that's ultimately what we're going to see represents the greatest danger right now to civilization, is not a single Tunguska type event that could be very, very devastating to a location or a region, but a multiple impact event that could be, more continental or even hemispheric, if not even global. Encyclopedia Britannica tells us that meteorite crater formation is arguably the most important geologic process in the solar system, as meteorite craters cover most solid surface bodies, Earth being a notable exception. Well, is Earth really a notable exception? Well, we have no reason to assume that Earth is being impacted any less than any of the other bodies in the solar system. What is different about the Earth, of course, though, is its active biosphere, its plate tectonics, all of the things that cumulatively will erase or degrade the evidence of an impact, whether crater or astrobleme. Craters become infilled with sediment. The raised rims will erode down so they're not as readily seen. They will get consumed through plate tectonics, through continental drift and subduction, the process of subduction, which is where one continental mass or one tectonic plate overrides another one. So you have erosion, you have deposition, you have tectonic processes, you have volcanic processes, you have seismic processes, you have biological processes. All of these things together tend to degrade and slowly erase the evidence of impact phenomena. So if you have a small impact that would create a depression in the ground, a few 100 feet in diameter, which there are many examples of, as a matter of fact, they're not going to last long. Now, the meteor crater in Arizona that's so obvious and so impressive, a kilometer wide, 600 feet deep, the estimated range of time is usually around 50,000 years old. So in 50,000 years, it hasn't degraded much at all. However, under other circumstances, you could have accelerated phenomena that would cause an acceleration of the rate at which one of these features is being eroded. But the point is this: between the Earth and any of the other solid bodies in the solar system, Earth has all of these other processes and systems functioning that tend to erase craters when they form. If those weren't operational, we could strip away the biosphere and the layers and layers of sedimentary rock that have filled in a lot of the earlier impacts, great impacts. There's no reason to assume that the Earth wouldn't look very much like the moon. And we know that the moon has had hundreds of thousands of impacts over its lifespan. So Earth is actually a much bigger target, a much more massive, both gravitationally and in its actual cross section. So we would assume, there's no reason to assume there wouldn't be just as many impact events on Earth as there is on the moon. But obviously the Earth doesn't look anything like the surface of the moon in terms of the density of the cratering. But that doesn't mean that the Earth hasn't been struck even more times than the moon has. And I think that, going back to the quote here from Encyclopedia Britannica, I think the idea would be that we're beginning to learn that the impact processes are extremely important. I would like to mention that one of our original sponsors at Cosmographia, CBD from the Gods, is following us here to our new podcast, Squaring the Circle. As many of you know, I've been using their products for going on 4 years now, and having tried a number of CBD brands, CBD from the Gods seems the most effective for my needs, which is primarily as a sleep aid and as a remedy for inflammation and associated pain. I use both the oil and the salve. My wife also likes their products, especially the salve, which alleviates the pain in her hands, which is the result of working for years as an electrician. If you've been thinking about trying a CBD product and experiencing the benefits for yourself, give CBD from the Gods a try. To learn more and see their product line, check out cbdfromthegods.com. Any purchase of their products helps our efforts here at Squaring the Circle to realize our goal of making this world a better place. Thanks. In the history, not only geology, but the biological history of the planet. What we're going to do now is we're going to talk about some of the simple processes. I've got a couple of cross sections here to help you understand the cratering process so that when you start looking at the images, you can understand better what we are looking at. All right, so these two diagrams, we'll start with the simpler case, showing us the processes of crater formation. So we've got two examples here. We've got a simple crater and a complex crater. Let's look. Some of the differences are subtle. Others are more prominent. If we look right here, we'll see that the complex crater has a central uplift. We'll also notice that there are these fracturing, these terrace formations along the rim here, which will show up as a multi-ringed structure. A simple crater, we'll see our first examples of craters in our gallery that we're going to look at will be a simple crater. Most famous example is Meteor Crater in Arizona. Let's learn some terminology here. Breccia is the fallback material. There's a whole bunch of stuff that gets thrown up into the air as a result of the impact, and then that stuff falls back to Earth. It can fall outside the crater or inside the crater. Obviously, the heavier and bigger stuff is going to get thrown less farther, and the finer, smaller stuff is going to get thrown farther. So a lot of the bigger stuff actually falls back into the crater. And you'll see here that there are two bottoms to the crater. There's the present bottom, which is actually not the original depth of the hole. The original depth of the hole is this bottom line down here. But then because of the material that falls back into the crater, there's the final depth of the crater as opposed to the transient depth of the crater, meaning it just lasts for a little while. Underneath, you've got the fractured bedrock. That's going to become important down the road when we're talking about exobiological processes, because fracturing in the rock allows the movement of water through the crust, which is very important. And when we look down here at the complex crater, we see that there is the two things that primarily distinguish it. One is the larger diameter, but then is the fault terracing on the sides and the central uplift. So this diagram here actually gives us a little bit more detail. And we have the ejecta being thrown out here. This is the excavation stage, which is the sole or only stage for a simple crater, right? So at the impact, a lot of material is thrown out. Some of it falls back into the crater. Some of it falls outside the crater. You have a shock wave that moves through the crust, through the rock, through the bedrock, and material can actually will move outward from the point of impact because of the pressure waves, which are represented by the white dashed lines here. We're moving outward from away from the impact point, the epicenter. If we go over to B, we see the end of the excavation stage and the start of the modification stage. So here you'll notice that the shock wave is moving out, but then it, in a sense, it's almost like the bounce effect. It moves out and then it starts coming back in as a rebound, and that rebound is concentrated toward the center, right at the impact site, and there is where you can see the beginning of the central uplift is beginning right here. We go to the C, which is the continuation of the modification stage, and you see the rebound effect continuing, and now we see the forming of the downfaulting along the rims, and we also see the descending ejectas falling back to Earth. Some of it's falling back inside the crater, some of it's falling outside. Now, of course, the distance that stuff is going to be thrown is going to be a function of the energy released upon the impact, and that energy released is going to be a function of the size of the object, the speed of the descending object, the angle of approach. All of these factors are going to play in, even the material forming the target rock. The final structure is what you see here, a central peak surrounded typically by a melt layer, actually a layer of vitrified rock in many cases. And then you see this terraced effect, which is the downfaulting that occurs around the rim. And that is often what you will see as a series of multiple rings. And then, again, the ejecta blanket you see is the dark gray area here that's typically going to be found almost like an apron around the original structure, the original excavation cavity. Okay, so let's continue on here, and we'll start with small craters. This is what we're going to do here. These small craters, I started small, and what I've done here is I've taken just a sample. This is far from every crater that we've now confirmed or suspected of being a crater, just to give you an idea. When what I've done is I've taken the diameter, the age, and in many cases I used a formula and that's given in the literature, and I calculated the energy released upon the impact, and that's based upon the size of the crater. Now, there can be a wide range of variability in that, but it is going to kind of get us in the ballpark so we can understand the intensity of the explosive phenomena that occurs upon impact. So some of these, I'm not sure exactly the precise pronunciation. I didn't have time to learn all that. But Alluel crater in Mauritania, it's a small one, 1,080 feet in diameter. It's about 3.1 million years old, but it's relatively young. It's undoubtedly not anywhere near as deep as it was originally. And the surrounding rim is not nearly as prominent as it would have been. You can barely make out that you can see right around here that you can kind of make out the impact blanket around it, the ejecta blanket rather. Let's see, we have a photograph in the next slide of the Alluel crater. Here's an oblique view. And if you look outside, you'll see that this is material that would have, this eroded material with the gullies in it, that would have been the blanket of ejecta surrounding the impact itself. Okay, let's move on here. Okay, this is the Kalkop crater, South Africa. Its diameter is 2,100 feet. It's how old? Not really certain, but it's less than 5 million years old. Well, let's see. So it's quite a shallow crater, and it's probably filled in. But you can begin to see that you can see this rim right here. That's undoubtedly what's left of the ejecta blanket, the collar, if you will, of material that's been thrown out. You see how there's this very distinct difference in terrain between this and this? So you've probably got several hundred feet of material blanketing the original terrain, the pre-impact terrain here. Now, the next one is the famous crater in Arizona. If you haven't visited this one, please do. This is a little old. I was using an older age for this particular crater. I think it was originally estimated to be about 50,000 years old. Then some studies suggested it was younger. Then some additional studies suggested it was actually closer to 50,000 years. So I'm going to kind of go with the more recent studies. Again, you can look at you can actually see this hummocky rim around it. That's the ejecta blanket. And there was actually things thrown out much further that, have scattered many, many miles from the crater itself. This is about about 600 feet deep, and it's about 3/5 of a mile or roughly a kilometer across. And it's definitely worth visiting. I did see a comment once online. Somebody commented about how amazing it was that the visitor center here came through intact after the impact. I said, well, it must have obviously been some good engineers on that project. So let's keep going here. Okay, this is Holaford Crater in southern Ontario. And here, this is a good example, I guess you could say, of an astrobleme, perhaps more accurately than a crater, because you can definitely see the circularity of it here. You can see that there's a forested area in the middle. It's not nearly as obvious as this, is it? But it's also much, much older, like 500 million years. So this crater, being in Ontario, has been swallowed up by glaciers multiple times. It's probably had all of its rim material ground off by glaciers. Glacial till probably fills up a lot of the depression itself. It's had plenty of time to erode. But here's, for this one, I went ahead and calculated the energy. For a crater about 1.46 miles in diameter, the explosive energy would have been around 42 megatons, which is about the same size as 2,800 Hiroshima bombs, atomic bombs, exploding all at once. Now, 42 megatons, little bit less than the Tsar Bomba, which was the most explosive hydrogen bomb ever tested by humanity back in October 1962, was it, or 61? 62, I believe. No, doesn't matter. But it was 61 or 62, tested by the Soviet Union, and its energy release was estimated to be about 50 megatons. The largest bomb ever tested by the U.S. was, some estimates put it at 15, most of it put it at 20 megatons, which would be somewhat larger than the energy released from the Tunguska impact. Okay. Then we have the BP structure in Libya. Its diameter is about 101.92 miles in diameter. Its age less than 120 million years. Explosive energy, now notice the difference. We've gone from 1.46 to 1.92 miles. Explosive energy is now up to about 125 megatons, which is the same as 8,350 Hiroshima-sized atomic bombs. So you can see that an impact of something of this size could be regionally very destructive. I'm going to get into, in a future episode coming up, I'm going to talk about a study that was done around Meteor Crater when it was formed, and the effects from the shock wave, the fireball, the pressure pulse that moved out from the impact, and what that did to the surrounding area. So anyways, then we'll go on. Chet, before we move on, you'll notice right here that it's got a central uplift, and you can see that there's a rim here, and then there's a second rim outside of it that's highly eroded, but you can still see remnants of that second outer ring. So now we get to something that's close to 2 miles in diameter, and we're getting large enough that we're getting into complex crater formations rather than just a simple crater. Okay, let's keep going. The Steinem Basin, Germany, 14.8 million years old, 2 miles in diameter, explosive energy, again, about in that ballpark. Now, these are only ballpark, but it'll give you an idea, 125 megatons. So now we're well beyond the power released during any hydrogen bomb. 125 megatons is going to be about 8,000 Hiroshima bombs exploding all at once. So obviously, any human habitation within this region is going to be completely obliterated if there was such a one. Well, of course, 14.8 million years ago, there wouldn't have been any humans, but there would have been hominids. Now, I've always been fascinated by this because you actually have 2 villages that are inside the crater itself. And you can see most of this around here would have been highly eroded ejecta material that's been gullied and so forth. Now, this is going to be Steinem Basin's going to put it right near the Fennoscandian ice sheet, so there's been undoubtedly, glacial meltwater flooding that has inundated this area. So there's probably been multiple times that this is actually could have been a lake. And you'll notice how the floor is quite flat. This obviously would not have been the original crater depth. It's been infilled with a lot of sediment. This is probably the remnant here of the central uplift. Okay, now let's go down to Australia. Goiter, which is less than 1.4 billion years. So it's very old. It's showing up in satellite photography. You can see the circularity of it. From the ground, you wouldn't even know this thing is there. But it's from the air that you can begin to... Now, a geologist probably would. They would recognize telltale features that could give it away. They would look at the fractured rock, typically overturned rock. If you see overturned rock around the rim, that's a good idea that there had been an impact there. If you go into the microscopic level, you'll see all kinds of proxy evidence for impact. One of the more visible features of impacts is shatter coning, and shatter coning occurs mostly in carbonaceous rocks like limestone and dolomite. When the shock wave passes through the rock, it creates a very distinct pattern within the rock, and I'll show you some pictures of that. Okay, so now some of these vary. Some of these I may have taken directly from the literature, from the studies of the publications, the scientific literature. So there will be some variation. This is 2 miles, but its estimated power is 125 megatons or 6,700 Hiroshima bombs. So, but the idea here is just to give you sort of a big picture view of this, not to give you anything super precise, okay? I might mention, by the way, that crater width is usually going to range between 10 and 20 times the diameter of the impacting object, just as a rule of thumb. So if you've got a crater that's 2 miles wide, that's roughly 10,000 feet, say, in diameter. So if you take 10,000 feet and divide it by 10, you're going to get an object 1,000 feet. If you divide it by 20, you're going to get an object between around 500 feet. So you could picture now that this particular structure was created by an impact of an object roughly between 500 and 1,000 feet. And we've got Brent Crater in central Ontario, approximately 500 million years old, again, diameter 2 miles. And here you're going to see, you can see this interior circle is now occupied by a couple of lakes. Right here is what appears to be a central uplift. You can see what appears to be the ejecta blanket out here around this area. It's probably eroded on the south side here. The other thing to keep in mind, again, is that this area has been subjected to repeated glacial interglacial cycles, and so glaciers are going to, cause extreme erosion of these features. Next one, though, is going to be a very classic simple crater, Chubb Crater. I don't know why we don't have a central uplift here unless it's been eroded away and it's maybe perhaps under the water. I don't know. But you can definitely see the very circularity of it. You can see a raised rim around it here. And you can see that that rim has been incised by erosion. And I don't know how far the ejecta blanket goes out, but if we look at this aerial photograph, we can see this lighter area right here. And it looks like it's more extensive to the northeast, which does that mean that the object came in from the southwest? Perhaps. Or does it mean that glacial processes have erased this area down here? Or I don't know. But you can kind of see this lighter area here that looks like it's probably the ejecta. Okay. Next, we have the Ouargzes crater, Algeria. We're getting up a little bit bigger. It's now like exceeding, and we're up to 2.174 miles. Age is less than 70 million years. And its, energy release is going to be in the ballpark of the preceding few that we looked at. All right. Next one is not an actual photograph, but it's a digital elevation model of the subsurface structure that you can't really see from the surface. And I visited the Flynn Creek structure with Brad Young. We've scouted out some areas and did find some examples of shattered and overturned rock that are an indication. But it's very old, 360 million years, approximately. That little sign right there means approximately. Explosive energy, because we're getting up, this one worked out to be a little bigger, 180 megatons. So you can see that an explosion of this magnitude we're now getting on the level where immediate devastating effects would extend out several hundred miles from the zone of impact. The next is a fairly new recent discovery, the Coruscant structure in the Gulf of St. Lawrence. What's interesting about this one, it's underwater at a depth of ranging from 131 to 682 feet. The diameter is about 3 miles. So here now we're getting up in the range of 180 megatons. So this is more than 3 of the biggest hydrogen bombs ever tested by the U.S. So this is now, an explosion of this scale could pretty much wipe out most of an area, maybe the size of Pennsylvania. The report on this that I read, they actually estimated that the impactor size was approximately 980 feet. Age pre-Pleistocene. Because of this is underwater, it's been very difficult to date this. So there's a huge age range. Some of the original ideas where it may have actually been terminal Pleistocene. It was put forth at one point as a potential Younger Dryas impact candidate. Whoops. The next one is Goat Paddock in Western Australia, less than 50 million years. Now we're up to a diameter of 3 miles. The flat bottom, now that could be both a combination of melting and infill. I haven't seen any core samples of this particular crater or subsurface studies, but if you look here, you can probably also see that there's, a raised rim and piles of material around it, like this area right up here looks interesting. And then you've got this smooth area right here. So something has eroded that away. This may have at one time been a lake. I don't know. Explosive energy, 500 megatons. Yeah, we're getting some serious environmental consequences now. The next one, we'll go back to Canada. The Gao crater, also about 3 miles in diameter. This is interesting because the central uplift is an island in the center of the lake. Now, in some of these highly eroded craters like this one, I want you to look at it. The circularity is still suggested, the original circular shape of the feature right after it was created in its youth. But you can see there's, been an extraordinary amount of erosion that has damaged, has compromised that original shape. So you have to kind of follow there is a hint of circularity there, no doubt, and that could be a starting point of research. But then you get into the proxy evidence of microspherules, iridium or platinum group metals associated with it, the overturned rock, melt, the microspherules that have maybe required 3,000 to 4,000 degrees Fahrenheit to melt. And then it's those kinds of evidence that will tell you that this is an actual impact event. So I want you to look at some of some of the topography surrounding it. And in this case, the debris blanket is not too evident probably because of repeated glaciation. Another view of Gao Crater where you can really, let's see, it's difficult to discern whether there's any debris blanket around it, but the island is undoubtedly part of the uplift. Pilot Crater, Northwest Territories, we're up to 3.6 miles. We're now looking at 70,600. Again, this could be 70,000, could be 80,000, it could be 60,000, but it puts you in the ballpark of the energy released. Think of it this way, 70,000 Hiroshima-sized atomic bombs exploding off. Again, this is very highly eroded. This is a highly eroded structure, and its circularity is not nearly as obvious as when in its youth. And again, this is Northwest Territories would have been completely glaciated. So you'd have had thousands of feet of glacial ice traversing over this feature. In fact, it may have even been completely buried under sedimentary rock that got removed by successive glacial interglacial cycles. Decaturville, Missouri, with a 4-mile diameter, age less than 300 million years. This one we're going to talk about in a future, probably the next episode, because one of the phenomena that's come up recently is the possibility of crater chains. Decaturville is one of several craters that appear to be in a line reaching east to west at about the 38th parallel. Well, here you can see there's a central ring. I don't see an uplift in there, but there is a ring, an inner ring and an outer ring to this structure. But being, a couple of 100 million years old, again, it's going to be highly eroded. Check out the explosive yield, about 1,000 or more than 1,000 megatons now. This is one of the, couldn't find any good images of this, but I did find this. This is one of those, notice the date, 320 plus or minus 80 million years. This puts it possibly in the same age overlap as the Decaturville, and it would also be one of this chain of 38th parallel craters. Notice this, that we're really getting the magnitude of this. We're at 4.3 miles in diameter, and we're getting up to 1,792 megatons. So 120,000 Hiroshima-sized atomic bombs. You're beginning to appreciate, I hope, the extraordinary magnitude of the energy released in a cosmic impact. There's nothing else that even comes close to these kinds of energies unless, at least on a planetary surface. Couture in Quebec, about 430 million years old. Now we're up to 5 miles in diameter. Again, look how eroded it is, right? So this is one of the things to keep in mind. If you're going to go crater hunting, don't just confine your attention to nice, well-developed, intact circle, simple crater formations like the Arizona crater, because some of them are going to be extremely eroded. They're not going to have intact rims anymore. And in this case, again, we're in Quebec, so this was under the ice multiple times. And here's just another view of it. And you can see here it's interlinked with a bunch of lakes and waterways and so on. A lot of the craters that were in the northern hemisphere have lakes in them. 5 miles in diameter. The next one, Gosses Bluff in Australia. This is always an interesting one to me. Its age, approximately 5 million years. So that puts it very close to what is known as the Hemphillian event, which was probably the last mass extinction event on Earth that was roughly comparable to the terminal Pleistocene extinction. And it occurred about 5 million years ago. And the diameter, about 5 miles. Energy, 2,800 megatons, or 186,000 Hiroshima atomic bombs. And this is one I believe that it's kind of now becoming a tourist destination in Australia, because there's a whole annular mountain, annular meaning ring-like mountain formation. Bagach, if that's how I'm pronouncing it right, in Kazakhstan, also impacted the Earth around 5 million years ago. So it could be that there was a clustered bombardment around this time that's associated with that Hemp-Hill mass extinction. Diameter about 5 miles. Now compare that to this. They're roughly the same age and the same size, which is interesting. And here you can really see the part of the debris blanketed around the central flat interior of the crater. So this may be a combination of an uplifted ring, broken rock, and fallback breccia that is piled up, which you can see if you go to Meteor Crater, you'll see something very similar to this, that there's large broken rock and fractured rock surrounding the crater itself. The next one is one that I've found really fascinating, Upheaval Dome in Utah. So I have visited this one several times with Brad Young, taken groups there as tours. And what you see here, let me jump to the next one. You can see here, look, central uplift, multiple rings. Now, what's interesting about this to me is that I think what we're seeing here is a juxtaposition of catastrophes. On the one hand, you've got the multi-ringed crater that clearly was at one time buried under layers of sedimentary bedrock, right? Oh, this is called, by the way, Upheaval Dome. It's about 6 miles in diameter, less than 65 million years old. But now look at the energy that we're getting into here. 6,000 megatons. This is now going to be something that where the consequences are going to be felt around the entire planet of an impact of this size. Now, you can see that there are layers of sedimentary rock that have been stripped away. So at some point, and I would argue that this would have been like prior to the uplift of the Colorado Plateau, because this is on the Colorado Plateau. This is in Canyonlands National Park or Monument, that you can visit. And there's actually a parking lot and about a mile hike. You've got to go up to the rim here. It's a fairly strenuous hike, and it's a desert country, so make sure you bring, if you go to see this thing, make sure you bring plenty of water. But so undoubtedly, I think what we see happening here is that you had the impact. It created a buried astrobleme, and then subsequent to that, you had large-scale erosional phenomena, meaning primarily water, that stripped away the overlying layers of bedrock, exposing the core that would have been hidden underneath. It's quite an impressive thing to see firsthand. I highly recommend it. In fact, we may be doing future tours there again, because we'd like to keep doing more tours to the southwest, because there's a incredible geological story to unpack in those Colorado Plateau, from Canyonlands to Arches to Grand Canyon to Monument Valley, Valley of the Gods. All of that stuff is extraordinary, and very extraordinary story there. So let's keep moving here. Next one, we've got Deep Bay, Saskatchewan. This would have been another crater that had been overwhelmed by glacial ice. And again, as we look at these, you can see how eroded they are. And again, this is going to be because of the presence of multiple glaciations. Well, we're getting up here. Deep Bay is 7.2 miles in diameter. It's about 100 million years old. we're really getting up there close to 10,000 megatons now. So again, we've kind of crossed a threshold where the impact events that we're looking at now, we're going to be looking at global consequences. Okay. So if you figure that this is 7.2 miles, let's just do a quick calculation here. If I go 7 miles, which is going to give us about 37,000 feet. Now, if I divide that, say, by 20, I'm going to get an object about 2,000 feet in diameter, roughly. Just roughly. 1,500, 2,000, maybe 2,500, but it's going to be in that range. Now, once we get up to between half a kilometer and a kilometer in diameter, it's now accepted by most scientists that we're getting into the range where we're going to be seeing global effects, climatic effects. We'll probably see, if it's a land-based impact, we're going to see a dust veil that could take years to clear out, which would have dramatic effects on the climate. If it's an oceanic impact, it could generate really enormous cataclysmic tsunamis when they make landfall. But I mean, just think about it. Look at here. You've got an explosion that's going to be, between 600,000 and 700,000 Hiroshima atomic bombs exploding all at once. Almost 10,000. If you look here, almost 10,000 megatons. So if you take just 10,000 and you divide that by 50, which was the largest hydrogen bomb ever detonated by humans, you'd have to have a couple of hundred of those going off all at once. Next, Vargeo Dome, Brazil, about the same size. Look at there, 7.2 miles, less than 70 million. That means that it could have been around the KT boundary, the dinosaur extinction event. Same explosive yield. And Spider Crater, Western Australia. Now it's up to 8 miles in diameter, and we're getting up to close to 1 million Hiroshima bombs once we get to 8 miles in diameter. Definitely going to be looking at global consequences. Sierra Madera, Texas, you can see it down here. It's a multi-ringed structure. This might be part of an uplift. I know, of course, it's highly eroded. 8 miles in diameter, less than 100 million years. The next one is Bustumtwi crater, which has a lake in it. This is in Ghana, in Africa. It's 6.52 miles in diameter. It's fairly young, 1.1 million years old, which means that would be young in terms of crater ages. There's been some interesting studies, particularly here, because the lake has preserved a very detailed record of paleoclimate change, so a lot of scientists have been studying deposits from the bottom of the lake and studying the water and so forth, because it tells us a whole lot about climate change in this area of Africa. Here's another Google Earth view of Lake Busumtwi. I call it that. There's different spellings of it, so I don't know exactly what the best one is. And then here's a ground photograph where you can see the surrounding mountains and the lake. Wells Creek, Tennessee, 7.4 miles. Now this one could also be the same age. You see 200 plus or minus 100 million years, which means it could fall within the error band of the Decaturville that we saw and Flynn Creek, because it's also arrayed along the 38th parallel. This is one I think could, notice the central uplift. Again, it's highly eroded. There is a quarry. When Brad Young and I went there, we talked to a landowner who owns land right on the rim of the crater. He knew about it being a crater. Said if we came back, he could get us access to the rock quarry where they're quarrying material of the central uplift, and we thought that would be extremely interesting to follow up on. Okay, next we have Zhemanshin in Kazakhstan. probably less than 1 million years old. We're getting up here now. We're at 8.7 million, 8.7 miles, and we're well over 1,200,000 Hiroshima atomic bombs. So all of the craters we're going to be looking at now, every one of them would have had global consequences. Perhaps related to regional mass extinctions, maybe not global mass extinctions, but definitely regional. Definitely climate changes on a pretty significant scale. Geological changes. Let's look at the next one. Ames in Oklahoma. We're up to 10 miles in diameter. Look at this now. When we get to 10 miles in diameter, we're looking at 2 million Hiroshima-sized atomic bombs exploding all at once. 10 miles in diameter. This could have been between half a mile and a mile in diameter that struck the Earth here. We don't actually have a photograph because it's buried and we don't really see it too well from the surface. But, geologists would discover the secondary effects of the crater if they don't see the crater itself. Again, which would be overturned rock layers, shocked quartz, microspherules, brecciated broken rock, down annular or ring-like downfaulting into rocks. All of these kind of things would be clues. And then if you can bring a cluster of these clues together, you can pretty much establish that it is now a verified crater. Next, we have however, age 3.5 million years, diameter 10.8 miles, explosive energy 40,000 megatons. So 40,000 megatons, we're now beyond the total megatonnage of the superpowers during the peak of the Cold War. So yeah, we are now beyond the stage of global thermonuclear war energies. And so an object 10 miles in diameter, 10.8 miles, it could be between half a mile and a mile in diameter when it strikes. So nobody has any doubts at this point that an object that large, moving at, say, 20 miles per second, which is a typical impact closing velocity of these objects when they hit the Earth, nobody's going to doubt that the consequences of that would be global in extent. This next one is a pretty interesting one. Arunga, Chad, 10.2 miles in diameter, multi-ringed. And I've got this note down here. It's part of a multi-impact event, and you can actually see a little bit of a second impact ring right up here, almost tangent. So this would have been two objects that were very close together. It may have been a single object that fractured, already had a fracture line or a fault line in it, and they separated as they were coming into the impact zone of the Earth. And there's actually a third. You can't see it up here, but it shows up on some Google Earth if you want to look this up and do your own research. I hope some of you do that. I hope some of you are inspired by this to get into it. And again, I don't even have half of the craters here. I could have doubled easily what I'm showing you in this. My intent here is just to sort of give you an overview of crater sizes, crater energy, the nomenclature, and being able to identify the criteria by which we use to identify these ancient events in the Earth's crust. Next one is also of Arunga, and here you can see central uplift, and then you've got this ring of uplifted mountains, and then you've got a downfaulted zone right in here, and then you've got another ring outside it. And Wooblo impact structure, if you see the Osage River, kind of follows this. There's a large buried circular feature here. It also is part of this 38th parallel chain that we're going to talk about in an upcoming episode, the crater chains and some of the very interesting and maybe even mysterious phenomena associated with cratering that we need to know about. But notice the age here, 335 to 340. I've seen others that have a very large plus or minus error bar next to them. So again, it's possible that it's in that same age range of 300 million years. 12 miles in diameter, meteoroid size, about 1,200 feet. I don't know, I may have taken that actually from the literature. Did not calculate an explosive yield for this, but you know it's going to be up there over 1 million megatons. Ghost's Bluff again, 14 miles. This one is really fascinating to me because of this. The central uplift is a ring of mountains. And the actual diameter of the crater, if we go to the next one, notice 2,800,000 megatons. So it's a very large explosion. But the next one, you can see what the area that would have been the original crater is out here. It's not this. This is just the interior uplifted ring. The original crater you can see is all the way out here. And from this figure, from this photo, I can't really make out where ejecta blanket would have been. But, you know, given its age, you know, there's been who knows what kind of erosive processes. With this mountain range nearby, I would have no doubt that a lot of the original crater depression would have been infilled by material eroded off of these mountains. Okay, the next one, Rias in Germany, fairly young amongst craters, approximately 15 million years old, 14.4 miles in diameter, 7,900,000 Hiroshima bombs. Now we're getting some serious global consequences. This is another view of it. And from the ground, this is what it looks like. Now, this is interesting because, you know, most people say tourists going along this highway will never have the slightest idea that they're driving through an ancient giant impact crater. The mountains you see here on the horizon are part of the uplifted rim, right? And the bottom being flat like this is undoubtedly had, you know, millions of years of sediment accumulating within it. So it's the topography of the original crater has been very heavily obscured. And one of the points I want to really try to emphasize here is that probably every square inch of the Earth's surface has been impacted. So that means that everywhere people are living on the top of what are highly eroded or, you know, obscured or even erased astroblems and impact structures without even realizing it, right? So this is sort of a different perspective on our Earth history when we begin to really immerse ourselves in the study of Earth's catastrophic history, which it has been profoundly catastrophic. And most of the considerations about global change, climate change, environmental change that are current do not take any of that into account. The real actual history of the planet. Manson impact structure can't show you a photograph of it because it's buried underground. It's in Iowa. For a little while, it was thought it might be a candidate impact for the KT or dinosaur killer event. Turns out it's a little too old and it's too small. Although it would have been regionally devastating. If you can see, if this is the structure compared to the state of Iowa, it was a safe bet that this impact right here, if it occurred in Iowa today, would pretty much erase Iowa. It would destroy everything in Iowa, southern Minnesota, you know, North and South Dakota would also be affected, Wisconsin over here. And of course, anything, say, within couple hundred miles of the impact itself, well, it's gone. You can see the diameter, 22 miles. That's getting to be pretty big. Notice the age. So it's a little too old. 66 million puts it right at the Cretaceous, but this is a little too old. And again, it's buried underground. So it's not observable. It's not visible from the surface. Okay. Houghton Astrobleme, Northwest Territories. This is going to be another one. that was under the ice. It's about 23 million years old, 14.5 miles in diameter. And again, it's not very evident, but, you can actually see there's a ring here, and then outer, there's actually another, like this is probably, if you look at this right here, this is probably whatever's left of the debris apron around the thing. But again, it's been under the ice multiple times, so it's going to have been very much obscured. But you can still see look at the circularity of the creeks and rivers around it, right? You can make that out. I've always been fascinated by this. Clearwater Lakes, about 290 million years old. You've got two craters, the West Crater, which is about 19.2 miles in diameter. The East Crater, about 13.2. Again, this would be under the ice. You can see that there's a central uplift ring, and of course, it's been highly eroded, and now you have a kind of a circular system of islands there. The smaller one does not show any signs of an uplift, although there may have been one there. At this size, it probably had one, but it's been obscured by glaciation. Check this out, though. The combined, so this, either we had, both of them appear to be about the same age date. So it was probably an object that came in, and again, like the Arunga, I believe it was, that we saw where it looked like it was an object that maybe split in two just before impact. Or two bodies that were traveling very close together when they encountered the Earth and simultaneously impacted. I'm inclined to think that they were probably a single object, but were actually separated by a major fracture line. And then as they came into the Earth's gravitational field, they might have separated somewhat. But take a look at this, because at some point when we get to the end of this, we're going to look at a map showing the Gulf of St. Lawrence up by New Brunswick and Prince Edward Island. And it's if you look at the Gulf of St. Lawrence, it's like almost like half of this, much bigger, of course. And this is almost like corresponding to Prince Edward Island. We'll look at that shortly. Teague, Western Australia, now named after the late Gene Shoemaker, who was one of the greats in, planetary research. 20 miles. I mean, now we're up to 200,000 megatons, right? 200,000 megatons. So that's many nuclear wars, global nuclear wars all at once. If I take let's see, what is this? This is 200,000 megatons. If I take the total megatonnage of the superpower arsenals all at once exploding, this is more than 20 times more powerful than that. So again, we're definitely in the realm now where there's going to be global consequences, right? And we have to begin thinking about this in terms of what this does to the biosphere, what this does to the environment. And we're really only just beginning because, you see, at what point do we cross the threshold where we're now talking about global mass extinctions, that the environmental consequences are so great that we are looking at, mass extinctions on a planetary scale? This, again, is still not even close to the crater size for the KT boundary at 66 million years ago, right? But it's still within the range where it's going to have global consequences. Now, what if something like this were to impact today? Well, I mean, obviously we're with a diameter of 20 miles, and this is an object that's going to be, 1 mile to 2 miles in diameter. So it's well within the accepted range of global climatic and environmental consequences. It could have an extinction level event on a regional, if not even almost a continental scale. It would ignite major fires on a large scale. It would create seismic events that could be felt on a planetary scale. It could have volcanic consequences. It could be enough to perhaps cause a cosmic winter, the onset of an ice age. Okay, so our next one, again, I'm not sure how to pronounce this. I don't know. I'm not even going to try. Katunki, I like that. Crater, Russia. Age, approximately 195.9 million years old. plus or minus a million years. Diameter is 25 miles. So again, and see, here's the thing. We're discovering these things now all the time. Remember when on our first excursion into learning about asteroids, we learned that on January 1st, 1801, Sirius, the first asteroid ever discovered, 1801, right? And how many impact craters did we know about in 1801? 0, right? So now the other thing to keep in mind is, again, we're talking about actual impacts into the ground that leave evidence in their aftermath. I'm not quite making out exactly where the crater is in this case. I'm thinking that you see this arc right here. I think this is it right here. This looks like it would be it. You can see the arc, right? You can see that arc coming around. You can see it's not unusual for rivers and creeks to flow around, especially if there's uplifted rims, to flow around, and then they will define the circularity and make it much more visible. This is a big one, 25 miles. Next one, Araguaina, Brazil, also about 25 miles. Now here you can see remnant of a central uplift. You can see, looks like an annular mountain ring there. You can actually see the circularity way out to here. So this is diameter 25 miles. Now, one of the things I think that we're only just beginning to appreciate the power of is LIDAR. And as we get more and more areas of the Earth's surface surveyed by LIDAR, who knows what we're going to begin to see hiding under the surface landscape. I think we'll probably see a flurry of confirmed impact structures coming up in the next decade or so. And then we have Karakul in Tajikistan, about 5 million years old. So you notice that we've had, 3 or 4 of them that have dated to right around 5 million years, which I find to be significant, again, because independently researching mass extinctions, I wanted to go back and find when was there a mass extinction that was on the equivalent level of the terminal Pleistocene mass extinction that occurred in the few millennia leading up to and including the Younger Dryas at the end of the Great Ice Age. And going back, the one that I found that seemed to be of a comparable magnitude was the so-called Hemphill event, again dated at about 5 million years ago. So it appears now that there's a clustering around the planet of events, impact events that occurred around 5 million years ago. How many more were there? I don't know. They didn't necessarily, that doesn't mean they all happened at the same time. And it's not like they would all have to happen at the same time to affect a mass extinction. One way I like to look at it is I use the metaphor of mixed martial arts fighting. Sometimes you might go in there and one fighter will get lucky, or because of superior skill will be able to come in and just one knockout blow, boom, the fight is over. Other times the fight is only won after a long period of attrition, or after multiple rounds. One fighter wears down the other fighter until finally the death blow can be delivered, or the fight is called and there's clearly a winner and a loser, right? So I think that some of the various scientists, whether archaeologists on the one end or paleontologists on the other end, have said, well, we're not going to attribute a mass extinction event to impacts because that would mean they all had to die at once. Well, no. What there could be is a whole series of events, constant clustered through time, maybe separated by thousands of years, but the end result, the cumulative result of that, is that the habitat becomes compromised severely enough and often enough that we see major extinctions losing their viability and becoming extinct. So this one, 28 miles in diameter, 65 million Hiroshima bombs released here. Obviously, this is going to have global consequences, is it not? The Siljan in Sweden, 31.2 miles. Explosive energy, 110 million Hiroshima-sized atomic bombs, all exploding at once. This is the remnant. And if you go down there and it's probably, present environment, probably beautiful lakes, well with great fishing in them, great camping, all of this around here. And how many of the fishermen, let's say out fishing in these lakes, know that this was a gigantic global catastrophe some 368 million years ago? Probably very few of them. Charlevoix, Quebec, again, another subglacial flood, or subglacial crater, about 360 million years old, 34 miles in diameter, 1,800,000 megatons. And here you can see part of it is completely erased by this lake here, but you can see at least half of the circular original feature still exists. Ackerman, Australia, we're still up there in that same size range. You can see the central uplift here. Again, highly eroded. Beaverhead, Montana, 40 miles in diameter, 2.6 million megatons. Global here. Now, an event of this scale happening now could essentially cause the extinction of most life in North America. And there would be secondary consequences, the dust fallout and the secondary fires, the soot, the seismicity, all of that would be very, very damaging and destructive. Manicouagan. Now, the original, you can see, is actually out here. There's a central kind of an uplift, and this is actually a artificial reservoir. There's a dam on some of these rivers. They're utilizing the topography that nature gave us through this highly catastrophic event. But look at here, 50 plus miles. So we're getting into explosive energy, 7,100,000 megatons. Now, this is falling very close to a late Triassic extinction event. And in fact, let's see, the next slide, we'll read that together. The late Triassic, which is the Carnian to Rhaetian stages, 237,000 to 201,000 million years ago, has a long history of geological research, although controversy remains over the precise definition of key subunit boundaries, including those defining the three constituent stages. But all that aside, within this context, at least 5 terrestrial bolide impact structures ranging from 9 to 85 kilometers in diameter have been identified at present-day northern latitudes. The proximal remnant crater aspects of which have been studied in increasing detail over the last few decades. So this is what I'm talking about again. It looks like clustered around. It's not saying they all happened at the same time. What it is saying, though, is that they were grouped, they were clustered in time. And within that range of this clustering of bolide impact structures, there was one of the great major mass extinctions in Earth history. It's considered often one of the great 5. And so it's very possible that just because a mass extinction event is spread out through time doesn't mean that bolide impacts didn't play an important role, if not the most significant role, in that mass extinction. Now, of course, the mass extinction is also going to be a consequence of the secondary effects of the impact as well. An impact of this size and scale of the Manicouagan is certainly going to be of the scale that would be required to induce a cosmic winter or a younger Dryas type global cold event, which, of course, could wipe out a whole lot of species that weren't adapted to a very cold glacial or Arctic climate. Chesapeake Bay astrobleme. This is age about 35.5 million years, diameter 56 miles. So again, we're way up there, well across the threshold of global effects. What's interesting about this, at least as a resident of Georgia, is that in Chesapeake Bay, when this impact occurred, the debris that was thrown up into the atmosphere, much of it was melted. And as it fell back to Earth, it assumed these aerodynamic shapes as it solidified, right? Those become tektites. And tektites are going to be composed of both the target rock material composition and the impactor, the bolide impactor composition. right? And this is how one of the geochemical tests of tektites. Now, there is a lot of this stuff that would have rained down over the southeastern United States at the time of this impact. But in the subsequent 35.5 million years, that landscape that would have been inundated with all of this, the debris falling back, particularly the tektites, which would have been melted material that's falling back to the earth, right? That landscape, number one, has either been eroded or buried. But just south of Macon, Georgia, at the fall line, the so-called fall line, which is an ancient shoreline, there's a very distinct topographical differentiation. And that land surface of 35.5 million years ago outcrops right there. So this is where you find the Georgia tektites, as they're called, or Georgiites. Now, in the next slide, we're going to see some examples of that. So these are some of the tektites. This was literally the splash material that fell back to Earth from the Chesapeake Bay bolide impact. That 35.5 million year ago landscapes outcrops right here in these counties that almost define the fall line right here, where we transition from Piedmont to ancient coastal plain, right? And particularly if you go down and you know exactly where that landscape outcrops, what you do is you go down there after a heavy rainfall, and this is oftentimes when you find these things laying on the ground. Of course, they're typically going to be covered in dirt, so you have to have a pretty sharp eye for them. But these are examples of Georgia tektites. And again, this was some of the stuff that rained back, the melted material that rained back down on the earth in the aftermath of the Chesapeake Bay impact. Now, interestingly, at the same time, apparently, I mean, so close in time that they could have occurred simultaneously. And by that, I mean within, days or a few years of each other, not necessarily tens of thousands or hundreds of thousands of years, but very, very close in time, was the Popogai in Siberia, which is an astrobleme, and you can see the remnant of it here. Again, it's just a scar in the landscape. 56 miles. Again, notice the age is precisely the same age of the Chesapeake. It's about the same size. Let's see, Chesapeake Bay was 56 miles, and this is 56 miles. It's also very abundant. It's one of the most abundant sources of diamonds on the earth, and that has to do 100% with the tremendous pressures of the impact. There had to be carbon-based rocks, and then you have the tremendous pressures of the impact. So you have the two ingredients you need for diamonds. So clearly, if these two happened back to back or simultaneously or very close to each other, they're on opposite sides of the world. And guess what? There was a mass extinction episode right around that same window. And I think it would be an obvious assumption to speculate that the mass extinction was related to the impact. So it's also what appears to be a major climate change signal as well. Then we go to the Kara impact structure, 35.5 million years. Again, diameter 75 miles. So it looks like we're seeing what could be interpreted as evidence of a clustered bombardment phenomena, and that bombardments, impacts of bolides and asteroids and things are not uniformly distributed through time. They're not linearly distributed, but they are bunched in time. And this could pertain on all scales of impact phenomena. And the Ackerman impact structure, also 56 miles in diameter, or 56 miles. I should have had this previous, trying to keep these in order of size, but that doesn't matter. 590 million years, but it's another big one. The next one is the Chicxulub astrobleme. Now this one, notice 66 million years, diameter 150 miles. And I have the plus mark because there's some controversy. Could be 150 up to 180 miles, maybe even bigger. But look what we're talking about here. 20 billion Hiroshima-sized atomic bombs, 300 million megatons. This alone, I think, would be enough to cause a planetary-wide extinction. There's also evidence, again, of clustered bombardment. And I'm not going to get into that because of the time limitations in this episode, but it also appears that there was a major impact that occurred in the Indian Ocean right at the KT boundary as well. Notice this, you can see central uplift, you can see multiple rings, and when I look at the next one, it's an artist's impression of the original. He's not showing the central uplift, which I think is a little bit of a mistake. He should have showed it, but he is showing the multi-ringed impact. Now, interesting about studies of multi-ringed impact structures, it appears as if there's a scaling factor that when this impact occurs, liquefies the rock, it begins moving out, just like, waves, ringed waves, like if you throw a rock into a pond, except that as it's moving out, it's cooling. So as it's cooling, it's becoming more viscous, and then it cools enough, and it essentially freezes wherever it happens to be when it crosses that crystallization threshold. Typically, the scaling ratio of these multiple rings falls right around the square root of 2, which is a ratio that we become very familiar with when we study geometry. So here's your artist impression of the Chicxulub impact crater. This next slide shows its relation to the Yucatan Peninsula and the Gulf of Mexico. So it says here this is a study that was published in 1996 in the Geophysical Journal International. The buried Chicxulub impact structure, is marked by a dramatic ring of sinkholes called cenotes if containing water, and adjacent, less prominent partial rings, which have been shown to coincide with maxima in horizontal gravity gradients and a topographic depression. You can see the topic depression is what they're calling the trough right here. And just inside that trough is a series of cenotes, sinkholes. These observations, along with the discreteness and spacing of the features, suggest a formation mechanism involving faulting in the outer slump zone of crater, which would thus have a diameter of approximately 180 kilometers or 112 miles. However, that is probably only the inner part of the crater. It's actually much greater than that. But this was from Yucatan karst features and the size of the Chicxulub crater. Okay, next slide, you can actually see the ring of cenotes here. Now, these are sinkholes. You know that most of the Yucatan Peninsula, well, pretty much all of the Yucatan Peninsula, is porous limestone. So what that means is that rivers flowing in the Yucatan don't flow on top of the surface, just like in, Cumberland Plateau of Tennessee. Limestone, porous limestone, it means the water tends to flow under the surface, and that's what's happening here in the Yucatan. The rivers flow under water. They're subterranean, okay? Interestingly, this is inside this rim, you have the whole huge mass of fallback breccia, slump features around the rim. And so what you have is all sorts of apertures and conduits and fault lines and fractures that water can move through. And if you look at this previous one here, you can see that half of the crater is in the Gulf. And there are actually tunnels, I guess you could say conduits, of water coming that bubble up out in the Gulf that are underground rivers flowing here. Now, what's interesting about these cenotes is that, this was Maya territory here, right? Maya had a whole complex system of eschatology, which is end of the world concepts. And one of the things that they did was they held ceremonies. Now, this is a photograph of a cenote. These are like sinkholes that have formed inside the rim. They're 100% a function of the gigantic buried crater. It's under about a half a kilometer of limestone rock, porous limestone rock, and this brecciated rock that was the consequence of the impact, right? So the water, it literally is like a gigantic labyrinthine tunnel system. And the Mayans believed that some of these cenotes were entrances into the underworld, which is certainly appropriate. A lot of them are accessible. Let's see here. Some of them are pretty amazing. You can go down into, some of them are set up, with accessibility. Look at this. Notice something here, that the surface opening is smaller than the actual cavity underneath. And, I think this is one of the ones that I've been in. I'm pretty sure it is. It looks like one of the ones. When I spent some time down there in Yucatan, I, of course, had to visit the cenotes. But you can go in, and typically the water, which has been filtered through the limestone rock, is very pure, very clear. And some of them, not all of them, but a lot of them, you can access, you can swim in them. This is one I went swimming in. This is a good example of, the surface opening is much smaller than the cavity underneath. And the day that I was here with my buddies, there's actually, you can see right here, there's the metal ladder going down into, that you have to climb down. There were divers coming out, and we talked to them for a while, and they said, yeah, people have been diving in this thing for years and years and never found the bottom. And, people have gone down, divers have gone down, gotten lost and never been seen again, because it's a literal maze of interconnected tunnels and things going through all this. So this is an entryway into the underworld. It's an entryway into the great bolide impact that ended the Mesozoic and launched the Cenozoic. And yeah, so you got to be careful. If you're walking in the middle of the night, it's dark out, and all of a sudden you take a step and boom. I think it was around 15 to 20 feet down to the water. I think what we did, we actually, if I remember right, we jumped off the edge into the water, and then, you climb back out the metal ladder. Here's the so-called cenote of sacrifice at Chichen Itza. And there is a bottom on this one. And for decades, if not centuries, Mayans were holding ceremonies around this. I'm going to save the discussion of what they were doing for another time. It's extraordinarily interesting, but their primary ceremony was commemorating the end of the world. And I found that to be very appropriate, given that the event here that led to these cenotes was the end of a world. Here's another view of the Well of Sacrifice, as it's called, because there was many artifacts that have been found in the bottom of this thing that have been collected over many, many years. We're coming to the end of this. Let's just jump ahead to a couple of the final ones. Sudbury, Ontario, very, very old. It's one of the largest, if not the largest, crater known on the planet at this point, 155 miles in diameter. The impactor size is estimated to have been 9 miles in diameter. I mean, look at the energy released here, 340 million megatons. Turns out that this site is mined because it's such a rich source of nickel, copper, palladium, gold, and platinum group metals, all of which are associated with and a byproduct of the whatever sorts of alchemy went on during the impact event itself. And that's something that we want to dive into and look at in more detail in another episode. And then finally, we get to the Vredefort structure in South America, which is the largest confirmed impact structure on Earth. Approximately 2 billion years. Now, there's probably larger ones, and I'm going to show you possible larger ones, but this is the largest confirmed. 187 miles in diameter, explosive energy, 630 million megatons, or 40 billion Hiroshima bombs. Now, 2 billion years, this puts it before the Phanerozoic. So we're back. I don't know. We can't really even begin to speculate what kind of environmental consequences this would have had on the Earth 2 billion years ago. Clearly, it would have been severe. Clearly, it would have involved seismic events. Clearly, it would have involved major volcanic events. There's probably been a lot of studies on this since I was looking at this. I began pulling this collection together in the 80s is when I got really, well, my interest in this really came, I think it grew out of the fact that as a boy, I was obsessed with dinosaurs and really got involved in the whole question of the mysterious extinction of the dinosaurs. And then after the discovery of iridium at the KT boundary back in 1980 by the Alvarez team, I found that was just electrifying. And the idea that the dinosaurs had become extinct due to an asteroid impact, I found just obsessively compelling. And that's kind of what launched my interest in looking at, this kind of phenomena. Another image of the Vredefort structure, South Africa, largest confirmed impact structure on Earth, also a source of precious metals and so on. You can see the circularity of it. There's this, rippled, it was so energetic that it's like it just smashed these rings together. You can almost see them here. You can make out the circularity. It would, of course, be highly eroded. Okay, so now, just to speculate, a couple of interesting things. The Nastapoka Arc here, kind of mysterious. I think it's very possible that we're looking at a feature that's a remnant of a gigantic impact that would have occurred, billions of years ago and mostly erased. The fact that these islands, I think they're the Solomon Islands here, could be the remnant of a uplift ring here. But about 280 miles, if you draw the circle on here, it's about 280 miles in diameter. Now take a look down here at Gulf of St. Lawrence and think back to some of the images, particularly the larger Clearwater lakes. I called attention to that. And the island, I said, was kind of like Prince Edward Island. So here you have a semicircular with what could be the uplift, central ring uplift. So just for fun, if you feel like, doing it, who knows what you can discover with Google Earth now and LiDAR imagery that's being more and more published. A lot of this stuff is published with no one really taking a closer scrutiny at any particular area. There's a whole realm here for, amateur researchers on their own to just make discoveries. Something that's interesting here, you can look, if this was a structure here, and this was an impact structure here, notice there's Manicouagan right there. Doesn't look so prominent next to these, but, obviously locally it would have been extremely devastating. Here's a map. It's already probably getting obsolete, and there's probably been a lot of new discoveries. I think this might even be 10 years old, but you can see the ever-increasing number of craters that have been identified in North America. In this little survey that we've done here, we've probably looked at only, maybe a third of the confirmed, if that. So there was a whole lot of them that we could have talked about, but we just didn't because we didn't have the time. So here's the same map. And here's a global map of confirmed impacts. You can go online and download this, and you see exposed and unexposed. So there's a couple now. One of the things to keep in mind is that, you can see how they're clustered. And this is important because there's a number of reasons. For example, there's a whole vast area here who the density of craters is very low, right? Look at these areas of South America. Look at these areas up here. Look at Greenland, right? Well, here's the point. I think if we were able to map all the craters on Earth, all the astroblems, we'd be looking at this kind of density over the whole map. You know what I mean? Okay. And that's important. And this next map, again, is already getting obsolete, but it kind of gives you an idea of the impact sites. And again, you see they're clustered, right? And there's reasons for that. For example, glaciers might excavate the overlying sedimentary rock and expose the underlying circular features, right? But the thing is when you look at the densest areas, I think if there was some way we could go back and reconstruct all the impacts that occurred on Earth from going back 3 to 4 billion years ago, just like the moon, we would essentially have a cratered surface with similar density of the moon, similar density to what we see here in these clustered areas. You'll notice rainforests of South America, nothing really to show there, but that doesn't mean they're not there, right? Same with Greenland, right? Same with the oceans. Right now we see that, look, there's an oceanic impact. Here's one, here's another one. So here's one over here. So we're starting to make more discoveries of these impact events on the bottom of the ocean. And I think this is going to be a very fertile area of future research. Okay, this last one is a closer in view of the Gulf of St. Lawrence. So I could speculate very easily that this might have been the remnant of a very large, very ancient crater. And you can see right here, by comparison, here is Manitkawagan, which is about 50 miles in diameter. Okay. So where are we going to pick this up? We'll pick it up by talking about what is the evidence for, we're looking here at evidence of these great impacts in Earth history. Right now, some of the smaller ones we were looking at have occurred since humans have been around, modern humans. But obviously the bigger ones haven't. Because if they have, well, we wouldn't be here talking about this. We would have become extinct. But the thing is that we have to consider, I think now, what evidence is there that these events have occurred since humans have been around, right? And then we got to narrow our discussion even a little more to talk about, is there evidence for impact events since humans have been trying to create civilizations? And the answer is most definitely yes. But then the question is, well, if that's so, then how many events have occurred and what influence have they had? What effects have they had on humans attempting to build civilizations on Earth? So we're going to look at two things. We're going to look at the evidence, the hard evidence, that there have been destructive bolide impacts, let's say within the Holocene. We'll narrow it down to the Holocene, the last 10 to 12,000 years, okay? During the time which we assume history has unfolded, human history. Second, we're going to take a deep dive into the legacy of mythology and stories that have come down to us from previous generations that certainly seem to be describing phenomena that could be considered profoundly catastrophic, that could have a lot of overlap with what we now know about the impact phenomena. Okay, so that's where we're going to be going in this, and I hope you stick with it to get the big picture of the cosmic history of this planet, the cosmic history of our own efforts to build civilizations on this planet, and the effects of these events on life, and what all this bodes for our future. And it does. It most definitely does. There are implications for the long-term sustainability of our future on this planet as a civilization, as a species. And that's where we're going to talk. That's what we're going to talk about. And we're going to discover that the evidence for cosmic events and cosmic impacts and catastrophes and so on is a whole lot more abundant than mainstream science has recognized up to this point. But thankfully, that's beginning to change, and that's what we're going to be diving into in the next few episodes of Squaring the Circle. So I hope you join me. Thank you for hanging in there with this presentation, and I'll see you in the next episode. Hello, Randall Carlson here with a short announcement about the multiple ways you can enjoy my new podcast, Squaring the Circle. If you haven't already done so, please make sure you watch Episode 1 to get a clear and detailed explanation on what you can expect from the Squaring the Circle podcast. All indications are that it promises to be quite a ride. In my effort to make this information available to as many people as possible, I am providing the following options. Full video episodes with ads will run exclusively on Rumble for free, and free audio versions with ads will be distributed to all major podcast platforms worldwide: iTunes, Spotify, Amazon, Google Play, and the rest. Ad-free episodes will air exclusively on my HowTube channel in exchange for a small fee of $7.20 per month. You'll get every episode of Squaring the Circle with no ads, plus you'll get exclusive access to bonus material available only to HowTube subscribers, which includes private live streams with question and answer sessions and special presentations on a wide-ranging variety of compelling, relevant, controversial, and interesting topics chosen by myself to challenge your thinking and possibly even inspire you. I will also feature special guests who are making major contributions to the evolution of human civilization and consciousness while advancing the critically important paradigm shift now gaining momentum around the world. In general, we'll be publishing 2 episodes of the podcast per week, and we'll also post 15 to 20-minute clips of each episode daily across our social media channels, for free, of course. We hope you'll follow us there as well. To all of my fellow seekers of knowledge, thank you for joining me on this amazing journey, and I'll be looking forward to seeing you again soon.